Imagine a dynamic 3D game scene where characters leap, landscapes morph, and objects glide seamlessly. This captivating visual is made possible by linear algebra, a branch of mathematics that deals with vectors and matrices. In the realm of video games, linear algebra is not just an abstract concept. It is the backbone that supports everything from character movement to realistic physics simulations. By understanding core concepts such as matrices and vectors, developers can create immersive experiences that captivate players. Visualize a simple 2D object on the screen, like a square. Using matrices, we can perform transformations such as scaling, rotating, and translating this object. For instance, scaling. To double the size of our square, we multiply its coordinates by a scaling matrix. Rotation. By applying a rotation matrix, we can turn the square around a pivot point. Translation. Moving the square across the screen involves adding a translation matrix to its coordinates. Combining these matrices allows for complex transformations. For example, if we want to rotate and then translate our square, we can multiply the rotation matrix by the translation matrix to create a single transformation matrix. This chaining of transformations is crucial for creating realistic movement in 3D games, as it simplifies calculations and enhances performance. Vectors are essential in representing positions and directions in 3D space. Each vector consists of three components, x, y, z, that define its location or direction. Here's how vectors are utilized. Position calculation. Vectors determine where objects are located within the game world. Velocity and forces. By using vectors to represent velocity and forces, developers can simulate realistic movements. For example, if an object moves at a certain velocity, its position vector is updated by adding the velocity vector each frame. A simple example of vector addition can be illustrated when simulating movement. If a character moves forward, represented by one vector, and then jumps, represented by another vector, we can add these vectors together to find the character's new position. Imagine creating a simple 3D engine from scratch using linear algebra concepts. In this engine, matrices are used for rendering objects on the screen. Vectors help simulate physics by calculating forces and movements. As we visualize this engine in action, we see how linear algebra transforms theoretical concepts into practical applications. For instance, when a player moves through a 3D environment, matrices handle the transformations needed to display objects correctly from various angles, while vectors ensure smooth motion dynamics. To delve deeper into linear algebra's applications in game development, several accessible resources are available. Online courses. Platforms like Coursera or Khan Academy offer courses specifically tailored to linear algebra for game developers. Game development engines. Explore engines like Unity or Unreal Engine that integrate linear algebra principles into their frameworks. Real-world examples of games utilizing advanced linear algebra techniques include classics like Asteroids, which employed vector graphics for movement and collision detection. By understanding these concepts, aspiring developers can unlock their potential to create engaging and dynamic game worlds. In conclusion, linear algebra is not merely a mathematical tool. It is an essential language that brings video games to life through immersive graphics and realistic physics. Embracing its principles opens up exciting possibilities in game development.